Hello and welcome to another episode of the Oxford Online Maths Club. My name's James, I work in Oxford, coming to you live from my office in Oxford. Today on the stream we're doing some square numbers, some sums of numbers, some numbers of numbers, and maybe some spirals if we get there as well. But first let's say hi to people in chat. Who can I see? Jamie's here, I can see Miles is here, and Erin and Herb. These are so far names that I recognise, but there might be people who are watching for the first time today, so hi if that's you. Somebody says thanks for the open day, which is on the script for this bit, that we recently did some open days. I'm glad you found them useful. If you want to join this live chat that's happening underneath, you can do that over at Vvox. There's a link on the screen and in the YouTube description. That's while we're live. We do it like that so that you can be anonymous if you want to. If you want to stick a name at the end, then you can. Hi to Akul over here as well. Hi to someone who's just put hi, which is fine. Anonymous chat's really nice, like that. I think some people have maybe got exams at the moment. Is that people in chat? Have you got exams going on as well? Hi Edward and Charles. Maybe not, because I figure most people in chat are in year 12 at the moment. And maybe you don't have exams in year 12, but maybe some of you got maths exams. I just saw on the internet that some people have got like a lot of those going on at the moment. Okay, I can see in chat. Oh, if I've got my chat set up correctly, maybe I do not. No, I do not. Right, there we go. Chat is now set up correctly. Just ended in June. Year 13, yep, year 13 have probably got some stuff going on as well. If you're in year 13 and you've got exams, commiserations about that. If you're doing GCSEs in year 11 or something like that, then sorry about that as well. Miles is in year 12. Nick's got a couple of weeks. So some people have just finished, some people haven't started yet. I remember last week someone told me that their CIE exams are all at completely different times of year, so different things in different places. 5/9 for the year 12 mocks, congratulations, that's very good. That's year 10, so GCSEs. Mocks is, there's a lot to decode in there, isn't there? Year 10 means that they're not yet doing their GCSEs, that's next year, but mocks means they've done a practice. 9 is the top grade. From context, it's GCSEs. 5 is how many of them they got. It's not 59 of them. You see, just the things that you learn to interpret as admissions coordinator around here. A-levels in 1 year and predicted grades. Applying with predicted grades, that is normal. Oh, hang on. We're doing them within 1 year. That's still fine with us. Yeah, if you're doing your A-levels within 1 year and applying with predicted grades, most people apply with predicted grades. This is not really supposed to be an admissions live stream, but obviously that's my job, so I can do admissions stuff, especially if it's easy questions. If you've got a complicated question in mind, you might get a better answer by emailing. If you email us, we reply to all of them, and it gives us more chance to look up links and things. CIE exams in a month, okay. Right, okay. So good luck with A-levels if you've got those going on, or GCSEs, or mocks, or getting ready for other exams and stuff like that. Normally I'd do a poll now, but I'm afraid I need to start with some sad news. Some of you might have known Vicky Neale, who is an incredible mathematician who worked in this department. I got the news that sadly she passed away earlier this week. I was a big fan of Vicky's. I'm still a big fan of Vicky's. I think Vicky's absolutely brilliant. She did lots of work in mathematics and in telling people about mathematics as well. She was on this stream a couple of times. A couple of years ago. So it was really sad news to find out this week that Vicky Neale's not with us anymore. I thought that rather than making this a very sad live stream, that's really sad, I thought what we could do is go through some maths that's Vicky Neale's sort of favourite, the things that Vicky Neale would talk about in a situation like this. Because I think Vicky wouldn't want us to be taking the week off. It's not Vicky. Vicky wouldn't want us to stop doing mathematics. That's definitely not Vicky. I think if Vicky were here, she'd want us to do some number theory. So I'm going to do my best. I'm not Vicky. I'm very aware over this week that we're really missing Vicky. I'm going to do my best at number theory. We're going to see if I can do, I know we're scheduled to do an hour and a half. I'm going to do as much as I can. And then we'll call it there. It's been a tricky week. Right, okay. That's why we've chosen these things to talk about. Squares and sums and spirals and numbers. Some of them are things that Vicky talked about on this stream a couple of years ago. So if you've been with us for several years, then you might have already seen them, but that's part of the fun, I think. Yeah, it really sucks. You might have known Vicky through UKMT stuff as well. She was quite involved in the UKMT. Some of the solutions videos that were posted for BMO videos had Vicky in them. She was also really involved with a lot of other maths charities as well, and wrote several books, which I think I will mention. When's an appropriate time to mention the books? I think it's now. I think it is now. So I'm not suggesting, oh gosh, again. So 2 books by Vicky that are really brilliant are Closing the Gap, which is a book that I've been recommending for absolutely years. I love it. It's about the twin prime conjecture. Are there infinitely many pairs of primes that differ by 2, like 39 and 41, except not that pair because 39 is not prime and I can't think of any others. Are there infinitely many examples like 41 and 43 of primes that differ by 2? Recently some progress got made by that. Vicky's book, Closing the Gap, is just a fantastic book telling the story. It alternates between the story and the maths to tell the story of what that was like as people got closer and closer to proving it, while also explaining the maths along the way. And Vicky has a more recent book called Why Study Maths. If I'm honest, if you're watching this live stream, you're going out of your way to find more maths content, then you maybe don't need to be convinced about how great maths is. But if your teachers doesn't really get it, or if you don't really get it, then, or if your friends and family are like, oh, what's the point of studying maths? And they're giving you a hard time, then this might be helpful. It's a very sort of sensible book explaining. Thank you. There are some twin primes in chat. 11 and 3 and 3 and 5. Yeah, those are great examples. Those are 2 examples. We're not going to list infinitely many now, but nobody knows whether there are infinitely many of those. We know there are infinitely many primes. Tutor's got a Vicky Neale book. It's going to lend to me. I've been lending Closing the Gap to some of my first year students, taking in turns to borrow that. Okay, those 2 book recommendations. One for you and one for your, I don't know, physics teacher, somebody who's like trying to why do you want to do maths at university? Erin's read Closing the Gap. It is really good. Okay, right. So I think it's time to do some maths. Let's do that. Yes. Is there any housekeeping I'm supposed to do at the start? No. Right. Okay. Let's go. Let's do some squares. So the question's really simple, which is the hallmark of a good number theory question. The question is, which numbers? Here are some numbers as examples on the board. Which numbers are the sum of 2 squares? I want us to explore this, and I want us to look for patterns. There's a possibility that you know the answer. If you know the answer, have some fun with it. Please don't post like the whole answer in chat. It's complicated, right? It's complicated. Please don't post the whole thing in chat. Let's have some fun with it. Like for example, this is on Wikipedia, so there's a Wikipedia page about this problem. Don't go and copy paste it off there, because exploring it and having some fun with it is part of why we've got it on the board, right? Like, why study maths? It's that exploring process and finding stuff out. Yeah, it's bad news for the department. Behind the scenes, Vicky was in an awful lot of committees and just did really good work on a lot of different things. She was the faculty's teaching advisor, the person who, she was really good at teaching, and she advised other members of staff about how to do teaching as well, which is a side of her that I don't think you see unless you were an Oxford student here, or if you were somebody else doing some teaching. Right, okay, let's get some examples of numbers that the sum of 2 squares. 2 and 3 is 5. 2 and 3 are not, right, okay. So we're gonna have a discussion about what a square is. So like perfect squares, maybe you'd like it if I called them perfect squares. So the perfect square numbers are 1, 4, I guess 0 is a perfect square as well. There, yeah, let's back it up slightly. 1, 4, 9, 16, 25. These numbers. I think I'll count 0. I'm not sure it matters very much. Can you use the same number, for example, 1 to get 2? Yes, you can. Yes, Nick, that's allowed. They don't have to be different. So, for example, 2 is 1 plus 1. Welcome to the Oxford Online Maths Club. 1 plus 1 is 2. Thanks, Nick. Yeah, 2 is 1 plus 1. That's the sum of 2 squares. Let's throw some more on the board. I'm going to do these in no particular order. So 13, an often unloved number, overlooked sometimes, but not today. because 13 is 2 squared plus 3 squared. So you see it's the sum of two squares. Again, people are being good in chat. People in chat are not posting in, like there's this theorem due to Gauss that's like the answer to this. Obviously, if Gauss is in chat, then I'd allow it, but Gauss is not in chat. Can we use 0? Yes, you can use 0, which I guess helps you to do the number 1. I'll let you use the squares of any whole numbers. How about that? Even negative numbers. 0 squared plus 1, 0 plus 1 is 1. Again, welcome to the maths club. 3 can't be expressed. Yes, okay, shall we prove that? Maybe it doesn't need a proof. 3 can't be written as the sum of 2 squares. That is true. I hope you can sort of see why. Most of the squares are too big. Most of the squares are too big to be helpful, and the small ones, not very good. 17 is 4 squared plus 1 squared. Yes, brilliant. Cool. What else have we got in chat? 3 can't be. Will be useful for Pythagoras when you have the gradient of the hypotenuse. Yeah, so in Pythagoras, Pythagoras is all about sums of 2 squares, right? A squared plus b squared is c squared. So I guess what we're discovering is the possible. There's something there, isn't there? So like I don't quite know what you mean about gradient of the hypotenuse. I sort of know, but there's some sense in which 13 has got something to do with Pythagoras in a way that 3 kind of doesn't, and that's very woolly. I'm being very woolly on purpose. 3 sometimes comes up in these triangles, and sorry, 3 doesn't come up in 13. Sometimes does. Can you make that precise? Oh, we've got more suggestions. We could do all the plus 1 squared ones. Yeah. All the square numbers are the sum of 2 squares. Yes, because 0 counts. I agree. I'm very happy with that. I'll fill in some square numbers. I'm allowing this. Yeah, I'm allowing this. I think this is good. Sometimes we have these arguments about whether 0 counts or not, but not today. I missed a couple in here. 5 is 2 squared plus 1 squared. Yes! I can sort of see that there's one community of people in chat who are going along the top row, and one community who are just pick and choose. Off you go. 58. Wow, 7 squared plus 3 squared is 58. Charlie, first one to tell me about that number, for example. It's pretty good. Okay. I'm getting a bit of a pattern here, maybe. Should the list start with 0? Yeah, okay, maybe the list should start with 0. There you go. Here's that. Nick's convinced me 0 plus 0 is 0. It's true. It's true. All squares plus 1 is a request I've seen in chat. I think I might have missed some. So I'm going to keep putting in all squares. And I'm sure I've missed some other stuff as well. Someone said something about Pythagoras. Again, Pythagorean triples. I think I know what you mean. Let's try this out. So maybe this kind of guessing numbers. I think I'll stop on the squares plus 1. Did I miss any? Yeah, algorithm. For the algorithm, I'm supposed to miss some of them so that I get more engagement in chat if I do something stupid, right? 8 squared is 2 squared plus 2 squared. Yeah, that's true. Squared. 72 is 6 squared plus 6 squared. Are people doing matching squares now? 72 is over there. 6 squared plus 6 squared. 16 is 0 squared plus 4 squared. Yep, thanks. Right, okay, so I've missed out some of the square numbers, have I? 36, 49, 60. Oh my goodness. You're making me work for this, chat. I missed 26. What's special about 26? Oh, it's 25 squares. 1 squared plus 5 squared. Right, yeah, okay. All squares plus 4. Right, Herb's got a system. The system passes a lot of the work to me, right? Because you could say all squares plus all other squares, and then, oh no, I've got to check all of them, right? So all squares plus 4 is true. I could go through filling in all squares plus 4. I guess I'm interested in where those are. What else have I missed? Oh, 18 is 3 squared plus 3 squared. Yes, correct. I mean, you know it's correct. You know that 9 plus 9 is 18. Have I missed 30? I missed 37. 20 is 4 squared plus 2. I like this. There's a lot that... keep telling me numbers that can be made by the sum of 2 squares, but if anybody wants to take the other side and tell me other numbers that can't be made as the sum of 2 squares, that'd be an interesting game as well. We've got this kind of pink cross next to 3. The pink's a little bit hard to see, isn't it? If anybody wants to take the other side and do the kind of work of checking that you can't make, or the smallest number we've got that's missing is currently 6. I think you can't make 6. Do we believe that? Oh, Charlie's doing all the big numbers. 64 and 9. 73, right, yeah, that's just off my screen, but there we go. 8 squared plus 3 squared. Yes, 15 can't be made. It's a big claim. We're going for 15. I'm going to put the pink cross in. 6, 7, and 11. Same side. Yeah, it's just that quest to say something different from everyone else in chat, right? Actually, everyone's picked different numbers so far, so this is pretty exciting. 2 squared plus 6 squared. You might also like to take the even bigger picture. The bigger picture is where you try and spot patterns, which is the fun bit of maths, if I'm honest. Spotting patterns of what's going on. Or even just trying to go like, I reckon this is true. This big thing. I've sort of thought of something the same size. Same side, same time, same thing. 7 squared plus 4 squared. 2 squared. Sorry, 2 squared is 4. You want to add 4 to... Yep, good. So I see people filling in the kind of pairs. You might think maybe I should make a table of like what the squares are and add them up and then reformat it somehow cleverly. Advanced line maths today went well. There's a pattern about columns. Somebody's taken my bait taking the bait. It's a fishing analogy. I throw out the bait is there for like, are there any patterns? And so I spotted a pattern. I don't know this pattern. 3 is missing seems very relevant. Implications about the status of n squared plus 3. That's a little bit vague. Would you like to be specific about the implications for n squared plus 3? Being very careful if your statement is large. Statements can be tricky. I think we're missing a few. More gaps as you go along as the squares get bigger and bigger. It's a good point. We've definitely got gaps so far because the small ones are easier to think of. Yeah, 20,000 is 100 squared plus 100 squared, right? Square numbers get big really quickly. There is this other effect that for the small numbers like 3, there's only a couple of squares you can use, whereas for 52, let's say, which is not so obvious to me because there's lots of square numbers I'd have to check, lots of square numbers I'd have to think about whether I can use 52 or not. So someone told me about columns, the 3 column, the 6 column and the 7 column. They are currently empty. I'm going to highlight them so that just to show you what they're talking about. So then there's a challenge for chat. Can you get anything in those yellow columns? Or can we work out that they're impossible? I'm going to put this in a sort of separate table of ideas. Maybe ideas need proof. But here's my ideas table. 3, 6, 7 columns are empty. And Miles, I'm going to put your n squared plus 3. I think you're telling me that it's impossible. I'm going to put that in the column as well, as an idea as well. Did we have other ideas? It's kind of like big picture ideas. I think people are telling me that particular numbers. I'm hoping that when people tell me things are impossible, they're telling me that there's actually some proof. So 24 is a bit interesting, I suppose. Should we zoom in on that? I sort of want to believe Herb, but also check what Herb's telling me. Yeah. There's gaps. I like this. Let's go. Gaps get larger, which I suppose you can interpret as maybe the density gets lower. Some sort of like how much black ink is there on the screen? Loads at the top, less at the bottom, maybe. Might be hinting about rules. In terms of the sum squares. We've got theories about n squared plus 6. I feel like I should start trying to disprove some of these. Ooh, it's tricky to disprove things. I don't know. In fact, I don't think it should be on me. I think it should be on chat a bit as well. N squared plus 6. I have an idea. Yeah, there's something going on. Someone's been invited to a sort of project. Hey, something to do with project to do with our promoted academic Olympic competitions in the English state schools. Sounds fun. Okay, cool. Oh, right, sorry, people are telling me more squares in chat, and I haven't been paying attention. 52, this one has done 52. I'm so pleased you've done 52. 52, oh, thank you. This feels like a supercomputer, right? I give it to the however many people watching, and you've got to find that. Whoever did 52, because I mentioned 52, thank you so much. Are you right, is the next question. 36 and 16 is 52. Brilliant stuff. And Nick's telling me about 34 as well, which is 25 plus 9. I'm going to write that as 5 squared plus 3 squared. By the way, 52 is... the reason I set the supercomputer on 52 is because, unfortunately, 52 is an example of n squared plus 3. Sorry, Miles. It's possible to adapt the idea, of course. This is a normal thing. I'm smiling, sorry, because I met Miles at an open day and I think Miles can take this. It's a good starting idea that needs a little bit more refinement, maybe. I'm not suggesting that we should refine it, really, to n squared plus 3, except 52. But maybe we can do something else. So it's really rude of me putting a supercomputer to... Oh, yeah, I missed a square number over here. Brilliant, that's really engaging chat. Thank you. Ooh, yeah, okay, so there's an algorithm in chat. Oh, yep, thanks. The first column seems like, hey. I want to read this one out, sorry. This thing, sorry. I don't know, but the first column seems like the difference in values between each square number... difference in values between each square number 1, 9, 25, 49... first column 1, 9, 25, 49. Oh, the squares in here. Oh, there's look like the Fibonacci numbers. So when you get a square number in the first column, you need to get a highlighter out, I think. When you get a square in the first column, it's not all of the squares over here, but some of the squares are over here. And there's maybe some sort of sequence to explain where are the squares. Where is the squares? Yeah, there's something going on there. Where are the other squares? I think we're playing this. I think we're playing where's the squares? 7 squared plus $sign squared is... Wait, can I infer what $sign is? 49 plus, you want to add on 16, 4 squared. 4 is the same as the dollar key. I could have, there we go. 7 squared plus $squared is 65. Oh, that's interesting. I already had that one. Can we try and do 33? Something vaguely Fibonacci-ish. So maybe try and attack 33. Okay, request from chat. Try and target 33. It's important for somebody's theory. We've only ruled out 3 numbers at the moment. I think the people doing some ruling out earlier, maybe I didn't give you enough encouragement and feedback, but you were doing really great work. I think I agree that these ones are impossible. You can sort of check by subtracting possible square numbers. This was suggested by Mars in chat, actually, that you could subtract numbers off, so you could check, is it square, is 1 less square, is 4 less square, is 9 less square, is 16 square. You can sort of check what's the possible squares. 33 is not doable, says Herb. Herb is busy doing, I imagine, a process like that to say that this is not possible. Nick can do it with 3 squares. So we have a completely different game with, I imagine, a different answer about changing this 2 up here to 3. Yeah, okay. Lots of people agreeing on 33. Yeah, okay. Realised I forgot to say, at that bit where I was forgetting about the admin, so it's rude of me to do this half an hour in, I forgot to say hi to Belinda. We've got Belinda in chat moderating today. Belinda is a current student who is helpfully moderating chat. Jump 1 from 1 to 9, jump 2 from 9 to 25. People are looking for the jumps in the square numbers over here. Right, we're going back in to play where's the squares. Jump 1, jump 2, jump 3, jump 4. Oh my goodness. Very good stuff, chat. I like that a lot. Jump 5, I got lazy and stopped writing numbers out at some point. I love that. So maybe not Fibonacci, but maybe the jumps get 1 larger each time to find these. Oh, I love that. Okay. I'm putting this on the ideas board. This is lovely. There are squares in the first column. Oops, with predictable gaps. Okay. I hope I'm not over labeling this chart, but 80 is 8 squared plus 4 squared. It's interesting to me how the which order they're coming in. Is that true? 64 and 16. Yep, makes 80. Yep. So far nobody's found anything in the 3, 6 or 7 column. That's not proof, of course, but it's going pretty well so far. 121 is a jump of 5. Yep, okay. Stacking up. We got some squares. Where are the other square numbers? All the squares of odd numbers. All the squares of odd numbers are in column 1. 1 squared, 3 squared, 5 squared, 7 squared. That's going in there, I think. I think that's going on the board. Let's put that on the board. All the odd squares. Sorry that I keep having to switch between the two boards. Sorry if it's giving you motion sickness as I move between the two. Where are the even squares? I'm going to start circling some even squares. You can probably point to them on your screen or something. Easier than describing it, isn't it? 2 squared is 4. 4 squared is 16. 6 squared is 36. Why is this so difficult? It's 8 squared? It's just squaring the even numbers. I can do this. It's over there. What's going on there, chat? Yeah, so Charlie knows about modular arithmetic, which is a word for looking at the remainders. And I think we might look at some remainders in a moment. Difference between squares being 2n minus 1 doing summations. Yeah, that's what I would do for this pattern people are describing in the first column. I would do something like that. The difference between two squares is a thing that you know so much about. You know the difference between two squares is just really good. You can factorize it. It's lovely. So here, jumping down, you need to maybe think about how many rows I've got. Oh yeah, there's some odd. Yeah, that's the sequence of odd squares in the first column people are describing. You can make all of those. Because you're allowed to use 0, so you can do 0 squared plus that thing. 48 is not doable, says Herb. Do I believe that? 24, yeah, cool. I think I believe that. You've told me it's 49 minus 1. Is there a claim in there? I've noticed that we've ruled out 24 and we've ruled out 3. I'm going to rule out n squared minus 1. 63 doesn't seem doable. Herb is targeting n squared minus 1. So Herb claims. Oh, switch to the ideas colour. At the moment, I'm putting things on the ideas board, whether we've proved them or not. We're going to come back in a minute, I think, and see which ones we reckon are true and which ones we reckon we can prove, which is sort of different, I suppose. X to 4 on the right. Oh, I'm not sure what that means, I'm sorry. I think you might be answering a question that I asked a minute ago. I do this sometimes, that I ask a question and then I forget about it, and then people answer it, and I've forgotten what the question was. I'm so sorry. 67 is not doable, says someone in the chat. Yep, I agree with that one. Okay. Being stubborn. There's something going on here. Right. What can I see then? Well, I guess what can you see for patterns? We've got this thing about columns going on. We found that the first column has got some square numbers in it. The second number doesn't look like it's got any squares in it. The third number doesn't have any sums of 2 squares in it. Then the fourth column has got some squares in. Columns 5, 6 and 7 are different, and then the last column there has got some squares in it as well. Oh, 9 minus 1 is a counterexample. That's true. Thank you for spotting it. So counterexample is a phrase people sometimes use if you've just seen this for the first time. I know the person who wrote that knows what that means, but if you've just seen the phrase counterexample for the first time, it means an example that is contrary to a claim that somebody's made. So they're saying that 8 being 2 squared plus 2 squared is a counterexample to this claim. A bit like before, we thought n squared plus 3 was impossible, and then we noticed that 52 was possible. Okay. This may be something about powers of 3. That's a refinement. That's when you take on board the counterexample. You say, well, okay, then I've changed my mind. And maybe other powers of 3 or something. Okay. I'm sort of putting words into your mouth there, sorry. I thought 2n squared minus 1 may not be possible. That's pattern spotting I like. We've only got a few that we've shown aren't possible so far, I think. We've been checking small numbers. Oh, 2x squared. 2 to the x squared on the right. Oh, right, so squares of powers of 2. Sorry, I'm so slow. Squares of powers of 2 feels good. We can maybe make that work. Like you've noticed, I guess you've noticed there's 2 squared and 4 squared. And we've used 8 squared as well. Oh, these things on the right, in the right-hand column? Yeah, on the right-hand column, these are squares of powers of 2. That's true. This is 4 squared and this is 8 squared. I got there in the end. You see? I asked that question, I forgot about it, you reminded me, we got there. This is 4, yeah, that's true. I guess you'd expect the next one to be, if it's 2 to the x, so we've kind of got a sequence here that goes 4, then 8, and you've said that's 2 to the x, and there's a possibility that it might be something else. Where are the squares? Apart from 1 and 4. Oh yeah, okay, so not 2 to the x, you mean not 2 to the x, but not 1 and 4 in the, yeah, not these ones, 1 to the 4 and 1 and 4 are also of the form 2 to the x squared. They're not in the last column, of course. And I've got a funny feeling that 144 is in the last column. I think 144 is 12 squared. I think this might just be multiples of 4. There are 8 columns. Something to do. Okay, let's talk about. No, hang on. Someone's put something really interesting in chat that I'm going to try and pass. I'm trying to read it. A and B are even. The a squared plus b squared is a multiple of 4. So you say hence multiples of 4 can be the sum of 2 squares. Let's be careful. You've shown that the sum of 2 even squares is a multiple of 4. Could it be any multiple of 4? For example, not 24, right? We think 24 is impossible, even though it's a multiple of 4. Oh, 74, 5 squared plus that. That's a lovely one. Oh, that's really good. I wouldn't have got there in ages. That's me getting distracted by some large numbers being squared and added together. Okay, so there's some gaps, but there's some really obvious gaps in these columns, 3, 6, and 7. Let's talk about that first idea. And so this one we're going to do a question, I guess, is it true? And can we prove it? So the key idea is going to be to think about what column things are in particular to think about what column the squares are in. So a squared plus b squared is the sum of 2 squares from which columns? And I think we saw that the squares, the odd squares, are all in the first column, and the even squares are either in this column, 4, or they're in column 8. We noticed that about the squares. I'm not sure we proved it yet. We noticed that. So the squares are either in column 1 or 4 or 8. Okay? There's not very many possibilities for the column. So squares are either in. The squares are from either columns 1 or 4 or 8, and then they're added. Right, we've got to think really hard now about what happens when you add things together. So if you've already heard about modular arithmetic or clock arithmetic, then you've already seen questions a bit like this, but I'm going to go through it anyway, because some people haven't seen clock arithmetic. if I take two things from column 1, like 17 and 33, and I add them together, well, in that case I get 50, which is in column 2. If I take two different things from column 1, 17 and 41, then I get 58, which is in column 2. If I take 1 and 9, I get 10, which is in column 2. If I take 25 and 49, I get 74, which is in column 2. Maybe you can see that whenever I take two things that are in column 1, Nick's off and away. Whenever I take two things that are in column 1 and add them together, I get something that's in column 2. Okay. In terms of remainders, the different columns are the different remainders when I divide by 8. There are 8 columns, so the kind of remainder keeps track of which column numbers are in. First column, that's obvious because the remainder is the number. But then in the second row down, 9, if you divide that by 8, the remainder is 1, it's in the same column as 1. 17, if you divide it by 8, the remainder is 1, it's in the 1 column. And these remainders add together nicely. So this is the idea behind modular arithmetic, also written like mod in chat for short. Also written like mod in chat for short, keeping track of those remainders. If I've got one number that's got a remainder of 1 when you divide it by 8, and another one that's also got a remainder of 1 when I divide it by 8, then when I add them together, I must get something that's got a remainder of 2 when you divide it by 8. The remainders add together nicely. Okay. Oh, that's a complicated claim. Right, we're going to put more claims on the board in a second. So there are only actually a few possibilities for the remainder. And this is a bit weird. It's either 4 plus 1, 4 plus 4, 4 plus 8, 8 plus 1, 8 plus 4, 8 plus 8. When I divide, so I take a squared plus b squared, but those squares, a squared and b squared, must be either 1 or 4 or 8, more than a multiple of 8. So when I add them, there's only a few possibilities of what might happen. 1 plus 1 is 2, welcome to the maths club. 1 plus 4 is 5, 9, so the remainder will be 1. 4 plus 1 is 5, that's 8, 12, so the remainder will be 4. 8 plus 1 is 9, so the remainder will be 1. 12, so the remainder will be 4. 8 plus 8 is 16. 16, so the remainder will be 8. Yeah, so you can do algebra with this. And the way that people normally write this, because this is quite a lot of writing, the way that people normally write this is perhaps a little bit confusing. But the way people normally write this is to write, where you're only interested in the remainders, is to write out things like 1 plus, I want to do a big one, let's do 8 plus 4. I don't really love any of these. The way people write this when they're just interested in remainders is to write out things that look a bit like nonsense. So 7 plus 5 is 12, but if I'm only interested in the remainders when you divide by 8, that means this is a kind of shorthand for the remainder is 4 when I divide it by 8. Which is the same sort of thing as saying which column is it in. Which is why it's relevant for our investigation now, because the columns are the remainders when you divide by 8. So if we're keeping track of which column it's in, then we just need to keep track of the remainder. So if you're doing arithmetic, then you can just throw away multiples of 8. Yeah, okay. Good luck with your physics mock tomorrow. See you, Charlie. Oh, hi, Gauss. Good to see you. I mentioned earlier that you weren't in the stream. 27 squared minus 1 isn't doable. Well done, Herb. I'm starting to wonder whether Herb's got some computer code for this. If you've just done 528 by, yeah. Good. Right, okay. This science of remainders is the punchline, I suppose, is that some remainders never come up. 2, 5, 1, 5, 8, 4, 1, 4, 8. You never see 3 or 6 or 7. And that's why when you add two squares together, you can never get something that's in column 3, 6 or 7. This one's true. I love it. Right, Pythagorean triples. People have been telling me about Pythagoras in chat for a while. Pythagorean triples is a very good thing to say, because the Pythagorean triples are all possible. A squared plus b squared equals c squared in a Pythagorean triple. The tricky bit is knowing what the Pythagorean triples are. That's not impossible. We can find some Pythagorean triples. Like, for example, oh gosh, this would be a good time to know a Pythagorean triple. 5 squared plus 12 squared is 13 squared. No, that's a massive number. Let's go 3 squared plus 4 squared is 5 squared. Yeah, that's over here. Something quite nice happens for Pythagorean triples. Maybe you can describe them? Oh, sorry, Ed. You could mute me and put subtitles on. Something nice happens, let's put it in words, when you've got a Pythagorean triple around. So there's this number that's really large that is one of my go-to Pythagorean triples, I guess, which is 5 squared plus 12 squared is 13 squared. I just think it's neat. We can put this together. Ooh. Ooh. So you can put that together as saying that you can write those in 2 different ways. That's pretty nice. Wait, hang on, there's something really clever in chat that I missed. You can multiply any sum of 2 squares by a square number to get another sum of 2 squares. That's brilliant. I love that a lot. It's very general. It's very mathsy. Multiply any... Hang on, I'm going to read this out. Any sum of 2 squares by a square to get a new sum of 2 squares. I love it. And I guess we can prove it as well, right? It's probably a little bit hard to prove this in chat, but I kind of know what you mean, right? If I write this times c squared. Yeah, I won't make you type this in chat. This is probably what you were thinking, right? Are there blackboards or whiteboards? This will greatly influence my decision of Oxford versus Cambridge, and I don't know which way around. It's whiteboards in Oxford. So no chalk dust. Which, yeah, means that I'm not permanently covered in chalk dust, so it's a bonus from my point of view. Can you square complex numbers to get Pythagorean triples? I mean, nobody's stopping you. It's debatable what your triangles mean in that case, if you're trying to think about triangles at all. But if you put complex numbers on your triangles, then you can make all sorts of weird triangles. I guess you're asking me about the sort of fantastic triangle that has 1 on this side, I on that side. I squared is minus 1, 1 squared is 1, those add together to give 0. So if you're into right angle triangles and complex numbers at the same time, then this gets pretty weird. You end up with this triangle with 1i and the hypotenuse of 0, which just feels weird. So, you know, beware if you're going in that direction, exploring the maths. Blackboard's outvoted whiteboard. I don't know if it's still there, but there's a blackboard in the loos of the Isaac Newton Institute, like next to the sinks. Next to the sinks, there's a blackboard, so that if you're washing your hands and you have a great idea, then there's a blackboard nearby in the Isaac Newton Institute. Blackboard is dark mode for lessons. Brilliant. What if we write the numbers in 9 columns? Would there be empty columns? Is there something special with 8? There's nothing special with 8. Well, I mean, this is quite nice, isn't it? 8 is how many columns I can fit on the screen. You can play the same games with 9. You'll need to check the possibilities, and as you're doing that, I'd encourage you to not just copy my maths off the screen, but with 9s instead of 8s. You're going to have to think a little bit about where the squares appear. So to find these numbers are called the quadratic residues, which sounds fancy until you realise that quadratic is a fancy word for square, and residue is a fancy word for remainder. So these are called quadratic residues. To work them out, you might want to do something like check all, or check the first few squares until you spot a pattern. Check what remainders they leave. We'll talk a little bit more about those in a second, but yeah, let's get some more ideas on the board and stuff. I love this, multiplying the sum of two squares by a square. Can I use that anywhere? So I multiply 10 by 4, I get 40, so that'll be 6 squared plus 4 squared is 40, which we already had. Hey! I've made my 4 and 2 mistake again. Yeah, 4 and 2, I keep getting mixed up. Yeah, 8's quite nice. I'm not going to go out there and say that 8 is a nicer number than 9, but this layout is a little bit nice. There's no way to auto-sign messages, I'm sorry, if you've got copy-paste. Oh, any complex number squared gives a Pythagorean triple. Oh, right, okay. Oh, sure, yeah, okay. Right, so you've noticed that the a squared plus b squared can mean the magnitude squared of a complex number? Yeah. Yeah, that gives you Pythagorean triples. Well, I suppose if the hypotenuse turns out to be, if it turns out to be a perfect square. I guess what we're discovering is, right, for the complex numbers fans, I guess what we're discovering is which numbers could possibly be the square of the magnitude of a complex integer. Wow, that was a lot of words. Complex integers, Gaussian integers, I guess. Possible squares of the magnitudes. Cool, okay. What happens if you do the sum of 2 cubes or the sum of 3 squares? Yeah, other games are available. Loads of stuff happens. Okay. I'd like to do a couple more things, I think. We've seen that some of the numbers in here in the column can be made and some of them can't. So there's still a question here about, once we've worked out which columns to look at, there's still a question, it's not just all of them, right? There's something complicated going on. There's a lot going on, to be honest. It's going to allow for this fact that you can multiply by any square number. Maybe that's okay. Here's something else you can do. You can multiply together any two sums of two squares. If x and y are each the sum of two squares, then x times y is also the sum of two squares. So this is a bit like the one that people said before. So if you notice that you can do 5 and you can do 13, my claim is that you can do 65. Oh, and where should we find? Yeah, you could do 65. If you can do 8 and you can do 13, why did I pick these numbers? Then you can do 104, which we haven't done yet. Pattern in the square numbers, odd number squared, multiple of 4, odd number squared, multiple of 8. Yeah, there is a pattern in the square numbers. That is a nice pattern. Odd number squared, multiple of 4, odd number squared, multiple of 8. Yeah, they go first column, fourth column, first column, eighth column, first column, fourth column, first column, eighth column, first column, fourth column. That sort of pattern is quite normal when you're looking at remainders and things like this. You end up getting nice repeating patterns. If the modulus is a surd, you can square the complex number to get an integer modulus. My gosh, that sounds really clever. That sounds really clever, gosh. Yeah, that would generate a Pythagorean triple. I don't think it generates all of them, all of the ones on the board, but their claim is something like, let me take your complex number idea and square it. I guess for the complex number, right, so your plan is something like a plus bi, where I is the square root of -1, a squared minus b squared plus 2abi, and then use that as the squares. And I think their claim is that you get a Pythagorean triple. And the algebra will then look like this. oh gosh, a to the 4, b to the 4, minus 2a squared b squared, plus on then 4a squared b squared. Aha, this is a squared plus b squared squared. That's true. That gives you Pythagorean triples. I like the final answer because the final answer's got no complex numbers in it at all, so it's not clear that it's not obvious that you used complex numbers to get there. But hey, hi everyone. We're doing number theory in memory of Vicky Neale, because she would want us to do number theory. What's not obvious is that I think this gives you all of the Pythagorean triples. I think this is a formula for Pythagorean triples that you've discovered. Huh, cool. That's sort of nice. Right, good. Okay. I think I want to prove this and then move on to something totally different. Oh yeah, I'm wearing a jacket. That's really throwing me. Okay, proof. So I'm going to move this to one side. Okay, here's the proof. Proof is one line. It's a good line though. I shouldn't bias you. I want to get your opinions on this in a second. There are x and y on the left. Each of them is the sum of two squares, and their product xy is also the sum of two squares because it is ac minus bd squared plus ad plus bc squared. Oh hi Nikita. I've got a poll. I would like to know this proof. Is it convincing, and do you like it? So there's a proof on the board that if x and y are each the sum of two squares, then you can multiply them together and you'll always get the sum of two squares. And the options are you convinced and do you like it? Or I suppose I'm only asking if you like it if you are convinced. If you're unconvinced, then I'm not asking whether you like it or not. So I suppose that's rude. There's like a fourth possibility. I'm unconvinced and I don't like it. Oh, unconvinced. Okay, unconvinced people, tell me in chat how I can make it more convincing. Yeah. How did you get that? 5 question marks is the top chat thing. So chat's settled on maybe unconvinced or maybe like this. Yeah, and those numbers are bouncing up and down a little bit, but unconvinced and like this is winning. Okay, that's nice. That's good to know. Good to get chat's opinion on things, right? Oops. There you go. How did you get that? With a thumbs up. So this is a little bit of a fake out because the I haven't seen unconvinced because I haven't seen the algebra, which is good. So the boring step in the proof would then be to actually go and multiply out all the sides of it and to compare all the terms and to say, yeah, it totally always works. And even then, it's probably not. Yeah, there's like a middle term. There's like a 2ab. Well, the middle term's weird because first outside, inside, last, right? You get this like a squared, d squared stuff going on, which is in here somewhere. Gosh. Here's the better reason. So it's related to the thing people were saying before. Sometimes you get results where you secretly used complex numbers, but it's not obvious from the final answer. This is an example of that as well. So if I take the complex numbers a plus bi has modulus. So modulus is like the distance from the origin. It's a bit like Pythagoras. And c plus di has modulus c squared plus d squared, square rooted. And there's something nice, which is that when you do the product of two complex numbers, the product of two complex numbers has modulus a squared plus b squared, c squared plus d squared. So if I want an expression for that, I just need to write out the square of the modulus of the complex number on the left-hand side. And complex numbers are easy to work with. relatively speaking. This thing here is precisely BC I. And to write down its modulus, I just need to square both terms and add them together. So secretly behind the scenes, I can't really remember this fact that I wrote out as the original proof, but I can remember how to multiply complex numbers. And I can remember that the modulus of a product works like that. This is why I wanted to prove this a little bit, because it's another example of complex numbers being behind the scenes as a good way of proving something or knowing something. Once you've got some facts about complex numbers, if you're doing further maths, then you get to learn about complex numbers at some point, and you get to learn about fun facts like what modulus really means. And they're hiding behind the scenes. Chat slightly took the wind out of my sails by proposing and proving a brilliant fact about Pythagorean triples with the same punchline that you use complex numbers. That was brilliant. Well done, chat. It's a live show. Anything can happen. But that was my plan for the punchline for the first hour. Yeah, it's really sad. Good. Was a question about whether I'm missing a minus sign. I squared is minus 1. The I squared term is this one here. I did the multiplying out quite quickly, but the I squared, that's you're referring to this minus sign, I think. That's the only time you get an I squared from that product. I think I did it right. A minus sign there doesn't scare me, because square it over there and it'll be fine. Okay. Vicky did this on the show a couple of years ago, and I thought it was worth doing it again. Right. Okay. Yeah. Okay. Oh yeah, I don't use the I. Right. Okay. Chat's cleverer than me. Chat worked out what that question was. Modulus is just the squares of the real parts added together. That's what they're saying. Good. Okay. Unsolved problems then from this first hour. I don't think we've proved or worked out things about these. We've got some outstanding questions. I think we're happy with that one. Not really sure about this one. The gaps looked quite big, and then people kept working and filling in the gaps, so hard to say. And there's other questions in there that people came up with where we change maybe 2 to 3, and we change squares to cubes, and we let you use maybe different powers or different combinations of things to play different versions of this game. This one I like because it's got a lot of sum of 2 squares, feels very Pythagoras-y. It's got that nice complex number link, and got a good answer. Okay, good. Miles thinks the gaps get smaller. Right, okay, I'm going to put both on the board. Higher up to 1. 26 is the only number 1 more than a square and 1 less than a cube. I think that's unknown. Right, I think that's unknown. Is that open? It sounds like a famous open problem. 26 is a really cool number. It's got this property in chat. Sort of unrelated to what we were just doing. Okay. When I put the further reading notes together, there's going to be a further reading note about sums of 2 squares. I might link to the answer, but the answer is pretty complicated. And also, it's never really about the answer. It's more about the fun we had along the way. Right, good. Okay, let's do something totally different for maybe half an hour. Who knows? It's another Vicky Neale classic. I don't think Vicky ever did this on the live stream, but Vicky did this with a lot of different people. So I'm now stealing it, putting it on the internet. Oh, is it proven? No, I think it's open. I think it's open. Right, somebody's going to Google that for me. Chat, please look up whether 26 is the only number 1 more than a square and 1 less than a cube. I think that's unsolved. Okay. So, just for half an hour then, or maybe not that long. This is an activity that works much better on paper. Ideally, I would have this on a printout, we'd all be in the same room, and I would get you to join the dots. It's a join the dot puzzle, but not in the normal way. You start with all these 72 dots around the outside, they're all numbered. Normal join the dots would be you join 1 to 2, you join 2 to 3, you join 3 to 4. Boring, rubbish. the idea here is that you do lots of separate line segments, and you join each number to its double. Miles can prove it. You see, Miles says yes, but I've forgotten which way around I asked the question. Oh, do people know this? People know this. Oh, okay. I know what I'm reading after this. Circle's going to be all lines, right? Yeah, okay. Other predictions? I'm going to join 1 to 2, and I'm going to do stuff like join 2 to 4. I'm going to join 3 to 6. I'm going to join 4 to 8, and I'm going to keep going 5 to 10, 6 to 12. And this takes a little bit of time, so while I'm doing this, I'd like chat to, I guess, tell me what's happening, or think of better ways to do this. If you remember, I think once we did something where we joined the dots of, we had maybe 2 lines at right angles, and we talked about what happens when you join the dots like this, moving along 1 each time. Has anyone done this? Does anyone know what I'm talking about? There was one, we did this on the live stream once. It was terrible because my internet was broken. So it came out as like a slideshow, like 1 frame a second or something. It was really, really bad. Tracy is closed. I'm gonna have to look that up. I hope that's not. I really remember that being an open problem. So the thing about getting older as a mathematician, some of the problems you learnt about when you were younger get solved while you're not looking, and then you realise that you're getting out of date. Staying up to date is really tricky. Okay. I'll accept any descriptions in chat about what's going on. If you've seen this before, you've seen it before. You might like to think about the graph that I'm drawing, if you like graphs, I suppose. A graph is where you have nodes that are connected by edges. The degree of a node is the number of edges that go to that node. So for example, this node at 24 currently has degree 2 because there are 2 lines coming out of it. I guess, non-trivial question. When I'm done, what will the degrees of the different nodes be? Ah, yeah, okay, so we're going to get around to 71 in a minute, and then we've got a discussion. Because the numbers are getting larger when I double them at quite some rate. I know what the rate is. Don't tell me what the rate is. They're getting bigger at twice the rate. Anyway, so 36. What should I do with this one? So what should I join 36 to? Ooh, we're getting something, right? We're getting something. Is it an exponential graph like e to the x or 2 to the x? So first, what are we talking about? I kind of know, but it's just a bunch of lines, right? It's just a bunch of straight lines. What are we talking about? Oh yeah, okay. Mod 71. I want to do mod. I have put a 0 in here as well, so I think I'll do mod 72. If you're into mods or remainders, it just feels normal that I should join 36 to 0. I think these ones are stepping. The ones that I'm joining to are stepping by 2 on the way around. I haven't got a 72, but I have got a 0, so it kind of feels natural to just join that one straight down. And then I hope it makes sense. I want to join 37 to 2. So I know that if you double 37, you get 74, not 2. That's kind of different by 72. It could be a golden ratio spiral. People know names of lots of spirals in chat. That's good to know. So I'm also trying to concentrate on doubling numbers. It gets harder to double the numbers when I get around here because now I've got to think a little bit. 41 doubled is 82. But the thing I actually draw it to is 10 because it's 10 more than 72. I think if you do this in real life with pen and paper, then it's easier to think of it as, you've got a ruler or something, and you're moving 1 step on the left here and 2 steps on the right. So 45 goes to 90 because it's 18 more than 72. 6 times 20. Is it 20? Is it 20? So you get this crisis of 46 doubled is 92, which is 20 more than 72. How's chat going? Vicky Neale talked about this at the open day. There's a great link. Thank you. 80, 94. Oh my goodness. 94, so I joined it to 22. Yeah. That question about degrees is, I think, still open. Still open as to what the degree is. Like how many lines go to each one. I'd have guessed, without giving it away, I'd have guessed 2. Gosh, where was I? 96. Because each line's got 2 ends, so probably the degree's 2. There's 2 of them at each point. It's not true. 96 goes to 24. Yeah, there we go. 49 goes to 26. 50 goes to 28. 51 goes to 30. 52 goes to 32 because it's 104. 104 is 30. Yeah. If you've just joined the live stream, then I think this is called slow TV. It's where something not very exciting happens very slowly. So these were big a few years ago, where people would just upload like a video of a long train journey. Yeah, just go to every other node, but it's a little bit hard to keep track of which node I was at. 58, 116, 44, yeah, good. I can just think about the last number. 46, 48, 50, 52, 54, 56, 58. Shouldn't be trying to talk about trains as well at the same time. Yeah, if you're having trouble sleeping at the moment, then maybe this is the kind of what you've been looking for. 66, 68, 70. Okay, and then I'm going to stop because I've got round. It's like images loading in the early internet days. Gauss, you're making me feel old. It's called a cardioid. A cardioid is a kind of heart shape, and that's what we've got. And in fact, it is a cardioid in some sense. I'm not really saying what it is. Yeah, like a love heart, right? There's this point here that's very interesting. I think people spotted that as we went round. Somebody spotted this. Lines diverge in the same point. Yep, there it is. I'm not sure it's all of the lines, but lots of them are involving something going on there. It's not all of them because of lines like this one. It's just like outside. But lots of them do go through that point. Take screenshots now. It's got some nice symmetry going on. The degrees of the nodes turn out to be either 1 or 3 with an exception, which you might have spotted on the way around. There's a code for it in chat, which is what you might type into Desmos if you want to see this. So Desmos knows about polar coordinates, which is pretty cool. Let's see if I can put this on screen. Can I put this on screen, Desmos? Ah, yeah, there's Desmos, good. So some people have seen this curve before because it is not that. Oh, also not that. What am I doing? I'm doing this. It's this curve. So Desmos is clever. It knows about these things called polar coordinates, where you define points in space by their radius and their angle above the x-axis. It's like a kind of radar screen. So you've got these lines coming out, which are labelled with positive numbers for the radius, and you've got these angles marked over here in radians on the screen at the moment. Then instead of doing y equals f of x, you can do r as f of theta as your curve, and you get nice curves like this. So people have seen this curve. Cardioid is what that's called. Cardioid, like heart. Herb says, want to build this out of string and put this on the wall. The original activity is to make this out of string. You need a circle to work with. You need to punch holes. Maybe with a kind of knitting needle is a good idea for punching the holes. and then you can put those around. My favourite coordinate system is oblate spheroidal coordinates, which hang on, ellipsoidal. Sorry, changed my mind. Oblate ellipsoidal coordinates. Thanks for asking. It's really good. Yeah, it's like one of those polar curves, right, that you might see in maths if you do polar coordinates. I liked this so much that I got, but I liked seeing it. Drawing it is a bit of a pain. So if you were here last week, you know that the thing I would like to do is to draw this with a computer. Computers are good at drawing lots of things one at a time. The advantage of using a computer, of course, is that also I can do it in colour. Use a different colour for each line. So if I do that, then I can have different coloured lines to show, going from around red to blue to green to orange to red again, which just looks nice. It would be a real pain to do this with like 72 colours of pen. But also what I can do now that it's in my computer is to increase the number of points, which would be a real pain with doing this by pen and paper. But with points, I can do something a bit more like that to really bring out the shape of what's going on there. So that's the same thing, but with I think about 200 points around the outside. I do maybe double it again just to see if we can get a nice smooth picture. There we go. That looks quite good. Oh, that's doing some weird, on my screen that's doing some weird, awkward picture things. Sort of degenerate, yeah, it's got this, it's called a cusp, which is this point here. It looks a little bit weird on my screen because of some artifacts to do with the plotting, but there's this sharp pointy bit. Someone in chat beat me to this because they've seen this, I think before. It's the coffee mug pattern. Sometimes if you get the light just right, the way the light bounces off a circular coffee cup, so you've got a circular coffee cup, a light above you, and sometimes you see this bright line at the bottom of the coffee cup. Works best with an empty coffee cup that's quite clean. So none of mine then. All of my coffee cups are either full of coffee or, anyway, never mind. So you sometimes see this bright line at the bottom that forms that shape. Something to do with complicated reflections off curved surfaces, right? Okay. Which node had only 2 lines? That is a great question. Oh, it hasn't quite appeared yet. There it is. Thanks for asking. Which node had only 2 lines? It was, I didn't see this coming, it is 24 and 48. Because I joined 24 to 48, and then a bit later I joined 48 to 24. So I drew that line twice. I think I actually did it as well, so I think, yeah, that line's in there twice. Oh, I've broken my row. Let's run away. Okay. Do I mean a donut? Yeah, cool. Or a donut. Right, back to the code, because the code's cool. What else do we want to try? So we've got a computer now. We can get it to do anything. The kind of more basic thing that I'll show you now while you're thinking of something for the computer to try is to get it to do, instead of doubling the number, to do something like just adding 10 to the number, which produces patterns like this. So if I take my number, let's put the labels back on. If I take each point and I join it to the one that's 10 more, then I've joined 1 to 11, I've joined 2 to 12, I think, have I done that right? Goodness knows, it's too hard to see. And you get these quite nice patterns, but they're a bit more predictable. So I didn't want to do this one out very, very slowly. Let's try throwing more. Let's try adding 20 instead of 10. This is a sort of slightly different pattern. And these are quite nice, but it's got this really rotational symmetry for kind of an obvious reason. You're kind of doing the same thing, adding 20 to each number, so it behaves the same way on the way around. I quite like the kind of 3D effect. Not intentional, but you kind of get a kind of 3D effect. Does it feel like a curve? Does it look like a curved surface? It's not just me, right? Looks like a curved surface? I don't know why. Yeah, cool, we got some suggestions in chat. Yeah, can we work out which line is repeated for a circle? It depends on how many points you are using. And I guess the answer is yes, you can work out which line it is. Okay, quickly look at my code. The code is bad, so don't look too closely at the code. So here we're doubling because it's doing I and j are which numbers to look at, and it's doing 2 times that. There's a request in chat for 3 times, which I will try now. I think we'll keep the colours. The colours are nice. So 3 times. Let's quickly switch. So 2 times first. 2 times first. Reminder. There's 2 times. Each number to double. If you instead connect each number to its triple, yeah, that. Ooh. Maybe that's giving you ideas. Maybe it's giving you. Maybe there's a suggestion. I think it's a kind of natural question after you've seen that. So connecting each number to its double, you get a cardioid. Connecting each number to its triple, I think this shape is called a nephroid. Oh my goodness. Sort of thing I should have known. Yeah, I think the shape is called a nephroid, which is, oh gosh, does that mean kidney shaped? So heart shaped, kidney shaped. At this point, when does it change? So it changes from circle to cardioid at quite a boring time when I changed my code to be adding or multiplying. So if I'm just adding a number each time, I get a circle. If I'm multiplying, then multiplying by 2, I get a cardioid. If I multiply by 3, I get this atoid, yeah. Nephroid, I think people say. I just Googled it. Vicky wouldn't have Googled it. Vicky would have known. Yeah, nephroid. I've checked it on Wikipedia. This will be in the further reading. It's just what you get when you roll a circle around the outside of a circle. So these are a little bit like spirographs, those toys where you have the cogs and you put the pen in and it draws the thing, only kind of exterior. Interesting. What shall I do next? Yeah, kidneys. One of the weirdest chat messages I've got. Ooh, 3D cardioids are used for microphones. Does that have to do with the gradients? Yeah, the gradients do change at different rates, and that can help you describe them. I think the natural thing to do next is, after we've seen cardioids with 2 and nephroids with 3, is to find out which internal organ does it look like if I multiply by 4 each time instead. And it's a bit hard to see that. It's one of those ones where if you squint it looks a little bit better. There's a mathological video with loads of these. Yeah, they're really good, aren't they? So I think I'm going to give you more points so that you've got something else to look at. Can you see what it's doing? Yeah, these are all really good in polar coordinates. The circle is the giveaway, right? I'm going to double the number of points. Yeah, that's a little bit better, a little bit easier to see what's going on. So we saw cardioid looks like a heart, then we saw nephroid looks like kidneys. I don't think any of my internal organs look like this. From organ, yeah, nasty. It's kind of got 3 bits to it. I'm going to turn off the numbers because I want to put more points in, and if I put more points in, then it draws a better picture, but also the numbers get a bit distracting. So I'm going to turn off the numbers, but keep doing more points. Yeah, a little bit like a brain. Cross section of a windpipe. Yeah. Any predictions? So pattern spotters in chat. We tried 2 and we saw a cardioid. We tried multiplying by 3 and we saw a nephroid with 2 blobs. We tried multiplying by 4 and we saw this kind of clover thing. If I try multiplying by 5 instead, what do you think is going to happen? If you're playing along at home, you can shout at the screen now for what you think will happen when I run this code with a 5 instead of a 4. But too late to tell me in chat because, yeah, more overly shapes. I've gone and done that. If I put on, yeah, let's switch this. The lines are a little bit too thick. With lots of points, the lines start to get a little bit confusing, so I'm going to change the line width. Bear with me. Yeah, that's a bit better. Thinner lines, so you can see more clearly. The thing we're looking at is made of lots of lines overlapping and being close to each other. So that still shows up, but if I make the lines thinner, then it doesn't ruin the rest of the space. Someone early on, I saw in chat, said the circle's going to be full of lines, and you're kind of correct. The circle's kind of full of lines, but there's these kind of accumulation envelopes that are really nice. Good, this is probably what you were shouting at your TV. Yeah. What about x squared? Brilliant question. And I saw you put that in chat earlier, but I wanted to build up to it for the kind of finale. We've got a little bit of chat here. Where has it gone? I thought I had this code. Right, we're going to write this code live. Writing the code live is probably not a good idea. Let's just go for it. So here's a loop. I need to tell it which one to join I to. I'm going to tell it to join I to, oh gosh, I want it to go to I squared, so I times I. and that will join it to j. So I'll draw a line from the I1 to the j1. I'm using loads of trigonometry for the circle stuff. Yeah, okay, squaring. Let's go. Ugh. Ugh. So person who said it's going to be full of lines, you get to say I told you so. Yeah, or I could do I star t for squares. That would be good if I expected to be doing cubes in a minute, then that's what I would do. So first time you see this, it looks hideous, which is a bit surprising because squaring is a nice thing to do. Really complicated questions about node. What's the degree of the nodes in this one? Yeah, it's not worked out well, has it? And then you start to notice that there are bits and pieces that are interesting. So there's this bit at the bottom with lots of nodes going into it. There's this kind of cusp thing over here. There's something going on here. There's a nice bit up here of kind of something going on. And there's some, maybe, I think I saw around here somewhere, something else going on. These artifacts are a little bit to do with the number of points that I've got. But I think that's an example of natural question, quite simple, really complicated answer. I'm always looking out for those. I don't have any I don't have a name for this shape, right? Because it hasn't made a shape in the same way that the other ones did. Yeah, not looking nice, is it? Spiderweb, we've got a big UGH in chat. UGH, spelled UGH, is what one of my tutors used to write on my work when I'd done. If you'd done a question correctly but using a mad method that had taken loads of work, then my tutor wouldn't tick it or cross it. They would just write UGH, UGH. So that's a flashback for me. Make the number of points a square number. That's a suggestion. No, sorry, not a suggestion, it's a request. Oh, it is a square number, it's 400. It's 20 squared. And that's what we got. Shall I make it 401? See if that's different. Make it not a square number. It's kind of better, kind of worse. Because that thing's now going off at an angle. And I don't really know what that thing is. So, you know, the number of points seems to matter quite a lot here. I'll just do 72. Just 72? No, I don't like that at all. There's too many, what's this bit at the top? What's that bit over there? 72. Weird. I've turned off the colour for that one. I can't remember if that was on purpose or not. It's a bit abstract. Is it art? I can imagine this being similar to some art, you know. Let's go back to, let's finish not on this note, but on a nicer note. Let's do something good that you can only really do with a computer, because you'll get bored if you do it with something else, which is to pick some sort of nice prime number, like 13. Put loads of points in, nice thin lines. Let's do them all in black, I think that's a bit more cool. The code in MATLAB, the code for black is the letter K, which is from printing, I think. Yeah, I think I'll leave it. I think I'll leave it on that one on the screen. That's a bit nicer. If you were spotting a pattern earlier, when I asked you, I'm going to multiply by 5, how many bits am I going to get? Now I've put in 13. Fill in each section with one of 4 colours. Yeah, it's planar, so yeah. Colouring this in with 4 colours. I think there's probably some. I mean, it does remind me a little bit of those. You can get these mindfulness colouring books where you colour in things. This has got definitely too many regions. Make an animation. Ooh, how do you want me to animate it? What parameter am I? Oh, so I've missed the request for square root x. Alpha titration. Cubes? I reckon cubes is going to be like squares but worse. Let's try it. Let's remove this. That's going to confuse me later. Cubes is like this. Wait. Not a disaster. Not the worst thing I've ever seen. A bit like the squares. Cubes is like that. With a request for square root of x. I'm actually not sure what it's going to do in this case. Yeah, let's just go for it, see what happens. Has it crashed? Wow! Yeah. Not sure what I expected, but it wasn't that. These bits are, I don't know where you can see them on your screen, but there's this kind of screen effect where you've got lots of lines quite close to each other. Oh, weird effect, by the way, totally separate. But when you put lots of lines together, the human eye can detect these hyperbolas. They're not real. They're not there. It's just straight lines. But you get this kind of optical illusion that it looks like hyperbolas in this kind of quite weird pattern that doesn't really exist or something. Right, good. Thanks for asking me about square root. Cubes looked better than squares, didn't it? That didn't seem right. Let's just quickly make it bad. 801? Actually, that's bad, right? Oh, it's not that bad. It's left-right symmetric. Why is it left-right symmetric? Oh gosh, I'm going to go down a rabbit hole. Cubes are left-right symmetric because cubing is an odd function. Yeah, so fifth powers will be left-right symmetric as well. Odd function. If you cube a negative number, you get a negative number. That's right. If you cube negative of a number, you get negative of that, the cube of that number. Similarly, if you cube minus 10, you get minus the cube of 10. This is fifth powers now. And it's got that left-right symmetry. So it's just as mad, but left-right symmetric, and that makes it look nice. Fourth powers will be awful. Yeah, hideous. Right. Is it called moire? When a line passes through and you can't see the motion, that's a moire. Animate number of nodes for x squared, see if you can spot a pattern. Okay. Animate that, they say. Right, okay. So loop it in the for, loop it for n, for different values of n. Tell MATLAB to draw it on each loop, otherwise it will get lazy. Tell it to pause for a little bit in between. Loop it for n is 100 to 200, so that going for 5, so it should be 20 pictures. And it's doing, I forgot to put in squares. So it looks horrible. So, quick example. This is 20 frames of awfulness because I forgot to make the most important change, which is to change it to be double. Let's try something else first, actually, just to see this animation idea. So this animation idea is getting MATLAB to draw lots of them from 100 to 200. These colons mean from and to. 5 is the step size that it's going to take. MATLAB's really good at doing these kind of loops like this. How many points there are? There's 13 times 5. There's this thing going on. Oh, that's awful. Why is that so bad? Oh, it's not got very many points. 200 is not very many. I'm running out of time on the clock. That's just starting to get good. Let's animate it from 400 to 500 and see if that's better. Yeah, okay, so there's the thing going on with so even in quite a nice picture, like this is multiplying by 13, it's got these nice 12 lobes or blobs on the way around. Even there, the stuff inside the circle it depends a lot on the number of points. You can see that jumping around and doing different stuff in between. I'm going to run it again. It's amazing that I'm still online while getting MATLAB to do animations. Some of the ones in between, it's got some extra sort of cusps that are not as densely populated, that I don't really understand where they are. I've got to think about that. Did you see them just pop in around the edges? These smaller ones? It's weird. Not sure I understand what's going on there. So I've got follow-up questions as well. I think I'm going to leave this as either further reading or following up. I've just noticed these 4 points. Sort of some symmetry going on here, maybe. Symmetries of these things are, well, they're just really interesting because out of all the things it could be, why is it something symmetric? Why 4, right? I'm multiplying by 13. What's 4 got to do with that? Am I multiplying by 13? Yeah, I really am. I'm multiplying by 13 and I've got something that's got 4-fold symmetry, I think. Maybe. Quite possibly. Oh, it's middle bit. I've got squares after multiplying by 13. That's crazy. Are they regular? I'm not even sure. Yeah, I've got squares. I've got parallel lines. Am I multiplying by 13? What's going on? I think I'll leave that there. The study of these kind of remainders, ooh, that's not really worked. Study of remainders is a good way to get into number theory because there's infinitely many numbers, but there's only finitely many remainders. I think I'll leave it there with these on the screen. In the further reading, I'm going to link to some other things to make and try at home that also involve remainders. but I think we'll stop the live stream around about now. So homework, you might like to try and make one of these with string, or make one by joining the dots in colourful pens at home. You might like to think about other remainders of square numbers. I saw someone thinking about remainders when you divide by 9. You might like to think about adding together other square numbers or other cubes or something like that. Either way, remainders are your friends. It did look a bit like a stained glass window with all the tiny bits and pieces, right? Good. Okay. Any final things before we wrap up? I think we're good. Thank you very much. Thank you very much for watching the Oxford Online Maths Club. It's been a bit of a tricky week here in the maths department, but thought it was important to still bring you some maths because that's what we like. We'll be back at the same time, 5 PM next Thursday, for the normal service of Oxford Online Maths Club. Maybe we'll see you there. Take care. Bye, Erin. Bye, other people in chat. Have a good evening, and I'll see you in about a week. Bye. Gosh, how many hours is it? No, I can work this out. 160. It's 166 and a half, which I said 2 weeks ago, and it's just so weird. Bye.